I'd like to make a few more comments about time domain or about frequency domain sampling and the DFT, and I want to go back to time domain sampling, which is something that we've studied and understand pretty well, just to make an analogy between the time and frequency domains. So first of all, in time domain sampling, we begin with a continuous time signal here, x of t, and we take samples at some sampling rate, fs. So 1 over fs is the sampling period, and we're taking these samples uniformly once every 1 over fs seconds to get a discrete time sequence that we'll call xn. So n is an integer. It goes between minus infinity to infinity. Now if we take the discrete time Fourier transform, this is something that we've done in the past. If we take the discrete time Fourier transform of the sampled sequence, then we get the dTft x of f, and that has a relationship to the continuous time Fourier transform of x of t through this relationship, which describes the concept of aliasing and frequency scaling. But yeah, and we've talked about this extensively in class before. So the idea is that we take the continuous time Fourier transform x of f, capital F, and we replicate that across the frequency axis at multiples of the sampling rate, and then we scale the frequency axis, normalizing by fs, to get the final aliased sampled spectrum. Now, if there is no aliasing, then it's acceptable for us to eliminate the summation here and just simply state that the discrete time Fourier transform is equal to the continuous time Fourier transform scaled in amplitude and in frequency. That's in the case when there's no aliasing. So the whole purpose of this summation is to represent the aliasing that occurs. Yeah, once again, this is the discrete time Fourier transform of the sampled sequence, and this function here is the continuous time Fourier transform of the original signal. So let's just keep that structure in mind, that when you sample in one domain, in the other domain we get this periodic replication of our spectrum, or of the signal. So now if we go into frequency domain sampling, let me just cover this up for a minute. We're doing the similar sort of thing. We start with a function that's a continuous function of its independent variable. In this case, it's a function of frequency. One of the differences between this case and the sampling, the time domain sampling case, is that this function that we're sampling is periodic, and we're taking samples uniformly spaced across one period of this function, and we'll call those capital XK. So again, we have this sampling relationship. So in the opposite domain, we would expect to see some kind of periodic replication occurring, and we derived this earlier. So if you take the inverse DFT of the samples, we showed that that sequence that you get is equal to an aliased version of the original time domain sequence. So again, what is this x of this x? This is the original sequence that has x of f as its dTft. In this case, the aliasing that's occurring is appearing in the time domain. And the important thing to note here is that the period of replication is equal to n, where n is the number of samples that we took over one period. We had a similar sort of thing happening in our time domain sampling setup, where the replication of our frequency function occurred at multiples of fs, where 1 over fs is the sample period. Similar sort of thing happens here. 1 over n is the sample period in the frequency domain, and so we get replication every n samples. Again, we could say that if there is no aliasing, in other words, if these replicas do not overlap, then we can say that this sequence that we get by inverse transforming the samples is equal to the original sequence. Let's take a look at some pictures that illustrate what's going on here. So again, what I'm going to show you are pictures of the replicated sequence, the aliased sequence, if there is aliasing. So first let's look at a case where there is aliasing. Let's suppose I start with a sequence that is length 16. And so here I've just drawn a picture of that. Remember, this is a sampled sequence. And here I am showing that same sequence shifted to the left by 10 steps. So I'm taking, so I'm using n equals 10 in this example. So we would be taking 10 samples in the frequency domain over one period of that periodic function, the dTft. That causes the replication to occur at shifts of 10. So I'm taking this original function, I'm shifting it to the left by 10, and I also shift it to the right by 10. And then I add up all of those replicas, and I take the answer over the first 10 time steps. So it's true that that these two replicas overlap, the original, the base replica, but we only need to pay attention to the aliasing that occurs between 0 and 9, that is the first 10 steps. And we can see that there is aliasing that occurs here, so this aliasing is in the time domain. And so what that tells us is that we haven't taken enough samples in the frequency domain to avoid this aliasing effect which happens in the time domain. To avoid aliasing, all we have to do is take more samples. So here, same example, but in this case I'm setting n equal to 18. So we have a sequence that's length 16, and I'm letting n be 18. So here's the base replica, here's the replica shifted to the right by 18, here's a replica shifted to the left by 18. We can see now that when we add these up, the replicas don't overlap, so there's no aliasing. And in fact, what's happening here is that we're getting some zero padding because the sequence that we're getting when we inverse transform those samples is has length 18. So we'll get the samples from 0 out to time 17. So the moral of the story here is, once again, if when we're approaching a problem to do data analysis, and we're going to use the DFT to do the analysis, we're given a set of samples. Let's say there are n samples that we're given, or let's say there are L samples that were given. Let me draw a picture of this. So here's my time domain sequence. It starts at time 0 and it goes over to time L minus 1. So this is x of n going from 0 up to L minus 1. When we calculate the DFT, we want to make sure that it's an endpoint DFT, and we want to choose n greater than or equal to L. This will make sure that there is no aliasing and that we have a sufficient number of samples to prevent aliasing from occurring. All right, we're back here to talk about time domain sampling one more time. Once we understand the concept of sampling, we can begin to make pictures like this. What this diagram shows is we have a time domain sequence here on the left and its continuous time Fourier transform over here on the right. We've studied extensively the concept of sampling in the time domain, where we go from a continuous time signal to a discrete time signal through this sampling operation, where we take samples at uniformly spaced times. That gives us an infinite sequence. And and then we can take the discrete time Fourier transform of that sampled sequence, and we know that there is a relationship between the discrete time Fourier transform and the continuous time transform, and that may include aliasing unless we have chosen the sampling rate sufficiently high and the signal that we started with was band limited. The same sort of diagram could be made for frequency domain sampling. In this case, we start with a time domain sequence x of n and its discrete time Fourier transform, which is a periodic function with period equal to 1. In this case, we're doing our sampling operation in the frequency domain, taking n samples across this interval 0 to 1. And we now know that the effect of sampling in the frequency domain is to cause aliasing to occur in the time domain. So this formula here shows us what happens with the time domain aliasing. Excuse me for just a minute. Let's see. So yeah, this formula describes the time domain aliasing, and if we take the discrete Fourier transform of that aliased signal, we will get our the DFT, which is samples of the discrete time Fourier transform. Another way of looking at this is we could start with our time sequence, calculate the discrete time Fourier transform, sample it, and then take the inverse discrete time Fourier transform to get the aliased signal. One of the things that we haven't talked about yet is that this aliasing formula tells us how to handle samples of x at negative time indexes. So let's take a look at that in this example. So here we have the aliasing, the time domain aliasing formula, and I'd like to apply that to this sequence here. Remember, this is a sampled signal. I'm just drawing it like it's a constant signal over a certain time interval. Now, the length of L, or the length of this sequence is L, and I think from the drawing you can appreciate the fact that L is less than n, or at least less than or equal to n in this example. So we will not have any aliasing in this case. So I've chosen n, this number out here. So what I'd like to do is draw several of these replicas, and I've already drawn them here. Let's just take a look at those. So here I have the case where the u equal -1 term in the sum, that is the original sequence shifted to the right n samples. We also have the u equal +1, so that's xn plus v, that's the sequence shifted to the left n samples. What this summation tells us to do is to add all those replicas together. Of course there will be more, but they're shifted outside of this picture. When we add all of those replicas together, we get this picture shown at the bottom of the page here. So this is the aliased signal, and we can see that no aliasing actually occurs because these replicas do not overlap. And then what we do to define x tilde, x tilde is defined as the set of samples between 0 and n-1 of the aliased signal. And the important thing to notice here is what happens to the samples that started at negative time indexes. Notice that those now show up over here on the right-hand side of the sequence, not over here on the left-hand side, because the sequence is always assumed to start at time 0 and go up to time n-1. So the negative time samples get wrapped around and they appear over here on the right-hand side of the sequence. The other thing that you notice is that we get zero padding, but it is in the middle of the sample set. So we have our positive samples occurring here on the left, we have a set of zeros occurring, and then we have the negative signal samples appearing over here on the right-hand side. So this is going to help you in the homework number 7, because there's a problem there where you have a infinitely long signal which you window to obtain a finite length signal, but some of those samples are at negative time indexes. So what you're going to have to do is take those negative time samples and stick them on the right hand side and do your zero padding in the middle.